Welcome to Roman numerals 8 and 9. Today we will be talking about acceleration and kinematic equations. The definition for acceleration is the rate at which an object's velocity changes. And hopefully you can tell that since velocity is a part of that definition, that we will be discussing acceleration as a vector quantity. So you want to make sure that you include the plus or minus sign or indicate a direction in some way. Also, you can tell that acceleration is a vector because of this arrow over the variable. That's how we denote vectors in our equations. Again, the definition for acceleration is pretty much just the equation written out in words. So when we talk about the rate, that always lets us know that we're going to divide by time. And then since it's the rate at which the object's velocity changes, I'm going to use the delta sign for my change and then the symbol for velocity. You can also substitute in final velocity minus initial velocity instead of that delta V if you prefer. This is going to make our units turn out to be meters per second from the velocity. And then remember it's a rate, so we're dividing by time. So we're going to be dividing by the seconds. And when we reduce that down, you would multiply top and bottom by the reciprocal, and you should end up with units of meters per second squared. On this next note, this will refer to objects traveling in the positive direction only. So keep that in mind. If an object is traveling in the positive direction and my acceleration is less than 0, then that velocity would be decreasing and I would be slowing down, and that might be called deceleration. However, if an object is traveling in the negative direction, it could be speeding up and still have a negative value. So you want to think about, I just left you space in these notes, what you think positive acceleration means and what negative acceleration means. Does it mean speeding up and slowing down all the time? Or could it mean speeding up in a negative direction or slowing down in a positive direction? We are going to have an activity to think about that, but I just wanted you to be aware that since acceleration is a vector quantity, those plus and minus signs are going to mean different things. And there are two cases when acceleration can be 0. Obviously, if you're not moving, then you are not accelerating. And then the other case would be if there is no change in velocity, which means you're moving at a constant pace. So you can still be moving, but not accelerating. This would be like the cruise control of a vehicle. For our next Roman numeral on the kinematic equations, remember kinematics refers to studying motion without considering the cause. So we are going to use these equations when an object is undergoing a constant acceleration. And using your units is really helpful, so I thought I would include a little chart here for you. Distance or displacement, remember we talked about that could be used as a D. If it's a vector quantity, you want to make sure and draw your arrow on top of it. But these equations will work for both scalar and vector quantities. Remember also that for a distance or displacement, we can use X and Y to indicate those directions as well and to kind of help us out with what our frame of reference will be. So I'm not really concerned with how you get the kinematic equations. I just want you to memorize what they are and look at them in the boxes. And actually, you don't even have to memorize them because lucky you in AP Physics, you are provided with a formula and equation sheet on every test. Remember, these will work for scalar and vector quantities. So if we're talking about the scalar version, you can leave this equation as is. The VF would refer to the final speed. VI is the initial speed, A is our acceleration, and T is our time. Or if we're discussing the vector version, you would simply put the vector notation over anything that's a vector quantity. And when I have no with a blank out to the side, this one has no distance involved. So if you're asked to solve for how far something moves, you do not need to use this equation because there's no distance. I do want you to be aware that you might see these formulas written in a different way on your equation sheet, so I'm going to go ahead and include that version here as well. I'm not sure why on your equation sheets they chose the X direction specifically, but just be aware on this extra subscript that you might see that pop up. And then also right here where it has a 0 as a subscript, that's the term not, and it also means initial. So you might see V0 instead of VI as an initial velocity. Again, not worried about how you come up with the equations. I just want you to know what they look like and recognize them. So I'm just going to scroll this down because you have your notes to look at. On this particular equation for our second one, notice that there is no final velocity or final speed. Again, for the College Board, they, for some reason, like the x direction, so they're going to specify that instead of a plain distance here, we're going to say x equals, because that lets us know it's the x distance. They also, you might be given a different starting point besides 0. So this would be if we were to add d initial into that part of the equation and then add these other terms that are listed. So you will also see that. And then we're going to add our initial velocity. Again, the naught is used as an initial, and then times time. And then our final term, we're still going to do 1/2 acceleration times time squared. And I believe that all of these subscripts, especially looking in the x direction, that's just a reminder that you want to look at things in one dimension at a time. So just be aware you're going to see these formulas in different ways. And then our last equation looks like this. I'm going to go ahead and scroll and point out that there is no time factor involved in this particular equation. The version that you'll see on your equation sheet looks a little bit different. Instead of saying a final velocity, it's just indicated as a velocity in a certain direction squared equals our initial velocity in that same direction. So remember the naught notation, the 0 notation is another way to write initial, plus 2 times the acceleration in that same dimension or direction that you're talking about. And then for a d, we're specifically looking at a displacement or a distance traveled from that initial position. So on your formula page, this is written a little bit differently. Just know that this term in the parentheses is referring to how far the object moved. Before we do some example problems, this next section reviews what you learned about in your summer assignment. So if we have an object that's falling, we get to live in this perfect, happy little physics world where we can neglect air resistance. So we're going to consider all objects dropped near the surface of a planet to fall with the same constant acceleration. And we call this motion free fall because there's no external forces acting on it. This acceleration is due to a gravitational force. So you'll see the notation A with the subscript of a g, or you might simply see a lowercase g. And this refers specifically to our free fall acceleration or our acceleration due to gravity. On Earth, this has a particular value. It should have been 9.8 meters per second squared, as you found out in your summer assignment. This is the value that we're going to use anytime an object is dropped. And it is an acceleration, so depending on how you set up your coordinate system, a lot of you saw that the downward direction ended up being negative on your graphs, and that's perfectly acceptable. You can make your coordinates any way you want to. If you wanted to say down was the positive direction, you are allowed to do that. However, it is standard to say that up is positive and down is negative. And then note that when an object is dropped, its initial speed or velocity will be 0. So on this section, you don't have to rewrite these equations. I just wanted you to realize that all of the acceleration values that we had before, whether it was a or a with the subscript of an x, are going to become acceleration due to gravity specifically. So if you wanted to rewrite that and include acceleration due to gravity, you can change that notation, or you can simply leave it as the a variable that we used before, and just know that you're going to plug in that 9.8 meters per second squared value for the acceleration. So I've got 3 example problems that we're going to do together, and then you'll see more examples come up in our labs in class. So we're going to start out with a car with a velocity of positive 24 meters per second is accelerated uniformly at a rate of positive 1.9 meters per second squared for 6.5 seconds. And you're asked to find the final velocity. So it's always a really good idea to write down everything that's given, and we're going to assign the variables to those values. So meters per second, remember it says velocity of, so that one's a really easy one to look at. However, you may not always be told specifically that a number is a velocity, so it's a good idea to use the units. We see that it's measured in meters per second, and that lets us know that it's a velocity or a speed. We do know later that we are looking for a final velocity, so you can label this with the initial or with the not notation, whichever one you prefer. You can do the 0 or the I. And then our acceleration is positive 1.9 meters per second squared. And obviously seconds gives us a time, and we are looking for the final velocity. So notice that there's no distance mentioned anywhere in this problem, so that's going to leave us with that first kinematic equation. And I'm going to use the easier version without those x's in the subscripts because I think it's a little bit cleaner. So I'm going to go ahead and write out my formula. And we're going to plug in our values. I know on that summer assignment you were supposed to plug in your units in the equation when you made those substitutions. If that gets a little too cluttered for you, I'm going to show you how we can do that off to the side and still make sure that our units check out, because you do need to show that work. So I'm going to say VI was a positive 24. And remember, I'm going to do my units to the side this time just to show you a different way. And my acceleration is positive 1.9. And then my time is 6.5 seconds. So I could calculate that out and get a final answer. So if you type that in your calculator, you should get about 36.35. I'm going to go ahead and stick to my sig figs. And it did end up being a positive number, so that lets us know we're still moving in that direction, and say 36. Okay. As far as the units go, I'm going to work those out down here. My first number was a speed, and it was in meters per second. And then in my equation, instead of substituting in a number, I'm going to substitute in meters per second squared for the units on the acceleration, and units of seconds for the time for those two variables. Now I can see that the seconds here cancel out with those seconds, and that allows me to add meters per second plus another number in meters per second. And once those units and dimensions agree, we're just going to say, yep, everything was meters per second, we're all good, and we can put that unit on at the end. So you can substitute those in with your numbers if you would like, or you can do them separately and then make sure you include your units in your final answer. So our next one, we have a student dropping a rock. In the future, you will not be given a hint, but you want to look for that key term of a drop. That lets us know our acceleration is going to be due to gravity, and we do not have an initial speed because it was not thrown downward, it was simply dropped. So let's list our variables. Since we're asked for the speed, we're only interested in the scalar version of everything. This I could say is a d, or we know that it's vertical, so if you prefer to label that as y, you are allowed to do that. Our acceleration is due to gravity. Our initial velocity, you can do v0 or vi. And then we are looking for the final speed. Hopefully you recognize that there is no time mentioned and you're not asked to find time. So we are going to use the equation that did not have time in it, which was our third one. And I know the notations are changing. It really is flexible. You want to find a consistent way to represent your variables that makes sense to you. So I set this equation up. We've got our final velocity squared, which is what we're looking for, or our final speed rather. And so I'm going to plug in my initial value, which was 0, so that's all going to go away. The acceleration value we were using is due to gravity, so meters per second squared. And the object fell 15 meters. So I know at this point my final speed squared is equal to 294, and I'm going to go ahead and put my units in. When I multiply meters times meters per second squared, that gives me meters squared over second squared. And a lot of you guys on that quiz on the first day, you plugged everything in correctly, but then when you went to take the square root of both sides, you only square rooted the number and not the units. Those get square rooted as well. So this is going to make our final speed equal to 17. And then when we square root those units, we see that we have meters over seconds. I'm going to set up this last one for you, and then you pause the video and try it and come back and check your answer. So I'm going to use the version of the equations that you'll see on your formula page. So I use those variables. I'm assuming that a plane is going to travel horizontally. So its initial velocity is positive 72 meters per second. Its final velocity, or the velocity that we reach at the end of our time interval, is positive 94 meters per second. And we have a time of 13 seconds, and we're looking for the displacement. So how far does the object move? Does the airplane go? And a reminder to add those arrows if you need help remembering those are vector notations. So first, think back to what all three equations had in common. We had said at the beginning that we were going to use kinematic equations for uniformly accelerated objects. Do you have an acceleration? The answer is no. So you need to find that first and then determine an equation to help you find that displacement. So pause the video and figure this out, see how you do. You can always come back and check your answer, and I will show you the complete solution. So a couple of things to point out. When you find your acceleration first, don't round too early. Don't say that that's 2, because that's drastically going to change your answers. You're not going to round and use your sig figs until you get to the very end. I also used the notation that you see on that equation sheet. So I said everything was in the x direction. We started out at 0. There wasn't an initial position mentioned. The seconds cancel out from my velocity and my time. And then the seconds squared and the acceleration would cancel out with this value because you're squaring the 13 and you're squaring the seconds. So those units would cancel and you're left with just meters. Since both of those numbers in meters are in meters, you can add them together and come up with your final answer. That's it. There will be another tutorial video to help you review kinematic equations if you need the extra help, and you can always come in and ask me questions if that's easier for you as well.